sure wanna be. Working like a dog all day ain't working for me. I wish I had a rich uncle that'd kick the bucket and I was sitting on a pile like Warren Buffett. I know everybody says money can't buy happiness, but it can buy me a boat. It can buy me a truck to pull. It can buy me a Yeti 110 ice down with some silver bullets. Yeah, and I know what they say.
What is the relationship between money and happiness? If we were to survey some random people and get responses measuring their levels of money and happiness, where would those points lie on this chart? Perhaps the simplest hypothesis is that there is no relationship. You might balk at me calling this no relationship because a seemingly straight line can be drawn right through the points. But think deeper. If these dots and this line are representative of the world, then does knowing someone's money measure help you predict their happiness? In fact, it does not. Know in advance someone who has a small amount of money? Then predict this level of happiness. Know someone with more money? Then you predict this level, the exact same level of happiness as the previous prediction. Knowing about the money measure does nothing to tell us about happiness. So what would a simple relationship between money and happiness look like? If we are lucky, a nice, easy mathematical relationship is a linear one, something where our survey dots of people might look like these, and a line drawn through them to characterize the essence of the relationship might look like the orange line here. Bayesian, Bayesian, Bayesian. So, if we want to get Bayesian about drawing a line through these dots, then what we do is allocate plausibility among all the lines that could explain the sort of typical relationship between money and happiness. We're saying this relationship is linear, and here are some representative lines from a posterior probability distribution. While we know how to create probability distributions for random variables, creating a probability distribution over a set of lines? Well, that might feel a little discomforting. That's okay. You actually have all the tools you need to do this already. I want you to think of a line as a parameterized function. Here is an example of that, where alpha is our intercept parameter and beta is our slope parameter. Given the parameters alpha and beta, we get a function of x such that f of x is a line. For an example of our parameterized function of a line, set alpha equal to 1 and beta equal to 1, and you get the following orange line. To get a distribution over multiple lines, we can just model alpha and beta as random variables, not known constants, and give alpha and beta their own prior probability distributions. Here are some sample lines drawn from a prior where the intercept, or alpha, is between -2 and +2, and the slope term, beta, can range from -6 to +6. So now we have all these lines, with each line being determined by a randomly generated alpha and beta. Let's assume that alpha being uniform between -2 and +2 is our prior belief about the intercept term, and beta being between -6 and +6 is our prior belief about the slope term of our line. Our job now is to create a generative DAG that links the equation of a line, as parameterized by alpha and beta, links the equation of a line to observations of xy pairs. A common way to make this link is to interpret the x value as helping to explain the observed y value. This generative DAG reflects that interpretation by placing the observed x value at the top and the observed y value at the bottom of the generative DAG. The arrow direction reflects our belief that x in some way causes or helps predict the y value. The relationship between x and y is assumed linear and is of the form alpha plus beta times x that we are used to. But this linear relationship only determines an expected value of y. We often use the Greek letter mu to represent this expected value of y. With expected value in hand, we then assume the actual observed y is normally distributed around expected value mu. Hence, the right-hand side of the y node indicates y is normally distributed with mean mu and standard deviation of 1. In a real data analysis, the standard deviation would also be modeled with a prior distribution, not a constant of 1. The prior distribution would then be informed by data. But we're going to omit the details of the standard deviation modeling to keep things simple for now. So, we see all the orange lines here with each one representing a draw from our prior distribution. And since we have no data yet, each line is one plausible relationship between a known x value and an expected value for y. But now that we have our generative DAG, we can introduce an observed xy point, shown here in purple, and this one point will then lead the generative DAG through Bayesian inference to reallocate plausibility to lines which are more consistent with the observed data. See how that works here. Draws from the prior distribution of plausible lines are on the left, and draws from the posterior distribution are represented on the right. Notice how the posterior is limited to lines which tend to be closer to the purple observation. This is how Bayesian data analysis works. For lines, we define our prior uncertainty in plausible lines, in this case by quantifying uncertainty in the y-intercept and the slope, and then we use Bayesian inference to reallocate plausibility to the lines that are most consistent with the data.
But what does all this have to do with money? You could think of it this way. Imagine that you're this caveman stick figure. You've got a nice fire there, access to nature. Is it possible for this guy to be happy? Well, maybe. But maybe it gets freezing cold at night, or maybe there's dangerous animals in the area. So we expand his lifestyle just a little bit. We'll give him some shelter. Is this a complete life for our caveman stick figure? Well, obviously not, because one of the basic needs is not met, which is food, so we'll give some food to the man. Is this a complete life? It's getting better, but most of us benefit from companionship, which I've represented here with this stick figure diagram of my wife. Now, what you have here, especially if these people are part of a village with strong social ties, really is the complete picture for human happiness, because they can laugh and love and learn and raise babies and actualize themselves and solve problems and create music together, all this stuff. And that makes sense, because most of human existence has been spent in these conditions, about 99% of it. It's just that we weren't around to see that. But just for a thought experiment, let's expand it a little further. Suppose Mr. and Mrs. Stickfigure hit the big time, and they expand their lifestyle a little more. So now they've got a nice symmetrical mansion with a Bentley and a Mercedes and a fountain there. Are they happier now that they've left the village of the sick people? Well, maybe, but maybe not, because they've probably severed a lot of social ties when they moved out to the country like this. But just to keep going, let's see if we make things a little better for them. What if they get a few more Bentleys, a few more Benzes, and some butlers to help out with all the hard work of maintaining this compound? Does this make them happier now that they have to put less effort into their lives? And if so, we should probably add a bed, because what could be better than lying in bed and having everybody serve you stuff and you could just gaze out at your luxury empire. And if that's better, we should probably add a bedpan and a catheter as well. Because what could be better than lying in bed all day and never even having to get out of that bed? And we could add a big TV so you could watch the world go by as you lie there. Now, hopefully, at some point, this fantasy broke, even though it's getting a little bit close to American life. And that's because adding more fancy shit and taking away effort from your life is not the path to a better life. And the reason is that effort and learning and all this other stuff that we've figured out by studying it in recent decades is really the stuff that makes us happier. Now, if you check out this next slide, I put these things into hexagons so they look scientific. These are the...
Gonna pack my lunch in the morning and go to work each day. And when the evening rolls around, I'll go on home and lay my body down. And when the morning light comes streaming in.
So if we buy into Mr. Money Mustache's theory of how money affects happiness, it is not the linear one we've been experimenting with so far. His suggestion is that once some certain level of money-enabled food, shelter, and social ties are met, that additional money does not really lead to increased life satisfaction, or at least not in a dramatic fashion. If we take some real-world data about money and happiness for various countries around the world, we see some support for Mr. Money Mustache's theory. On the horizontal axis is GDP per capita. We will consider this a proxy for individual wealth. On the vertical axis is the aggregated results of the World Happiness Survey from 2015. In that survey, they rank each country on a scale from 0 to 10 for life satisfaction among the country's citizens. Now, we are doing this exercise for fun and education, so do not put too much faith in our findings here, even though our findings will correspond to Mr. Money Mustache's theory. Happiness is just such a tricky thing to measure. The best causes of happiness, like friends, community, health, and life philosophy, are all excluded from our relationship here. Any rigorous study of happiness would have to include these other factors. Throwing these details aside, I now seek to confirm the Mr. Money Mustache hypothesis. But since these points are not linear, I do a trick. I take the logarithm of the GDP values and use this as my new x-axis. Notice this transformation effectively puts the points in a more linear format, which we can handle with basic tools from our mathematical toolbox. However, before jumping into modeling my generative DAG, I do have one more trick to show you on this graph. Consider how you might express your uncertainty in the y-intercept of a line which goes through these points. It seems hard to do, as values can be negative or positive, are sensitive to changes in slope, and lack real-world interpretability, as there are 0 countries that have 0 GDP. Simply put, I have no great knowledge about what this point should be, and I am very dubious of my ability to come up with a meaningful prior for it. Alas, all is not lost. A line can be defined by any given point and any given slope. So let's not specify a prior for the y-intercept for this set of data. Let's transform the data one more time so that the y-intercept becomes meaningful. If we just move all the points to be horizontally centered on the y-axis, then this new y-intercept represents the expected uncertainty for an average wealth country. I can do that. On a scale from 0 to 10, I'll say 5. The average wealth country has life satisfaction of score of, say, 5, with a standard deviation of 2. That's my best guess for the expected life satisfaction score of an average wealth country.
I wanna know what became of the changes we waited for love to bring. Were they only
right, so if you followed the video, you could copy this link from the show notes or from the video itself, and we will bring in this code into our studio. And we copy and paste it in there, and we got a lot of code, and I'm just going to quickly run through it. So this indicates where we got our data from, talking about life satisfaction. And now we do our preliminaries, load the packages we need, all good. The data set we're going to use is available from my GitHub account, so you could just download that. Control Enter and create plot.df, and this is really what we're going to be working with. So we look in it, and we can see we have 4 columns. 1 is country, 2 is life satisfaction, 3 is GD per capita, or our money measure, and this is our transformed X value. So instead of using GDP per capita as our X value, we will use X trans. And you can see how we defined X trans right up here. We took the log base 10 of GDP per capita, and then we subtracted the average value to center those values on the y-intercept or the y-axis, so we can put a prior on our y-intercept. We can look at the data. Here's a plot of that curve, the Mr. Money Mustache hypothesis curve, where as money increases, there are diminishing returns in terms of life satisfaction. We're now going to use this generative DAG to fit the data. I will graph the generative DAG. We'll zoom in on it, and you can see our observations of life satisfaction depend on this expectation mu, which is expected life satisfaction. That is just a linear function of our alpha term, our beta term, and this transformed X value, which has been logarithmed and centered. Also notice that I did put a prior on the standard deviation sigma here, and a gamma 2,1 prior will easily get us 2 units above or below our average expectation for life satisfaction. Since life satisfaction is scored from 0 to 10, 2 seems like a very reasonable standard deviation to be centered around. We run line 73 to get our posterior.
Say it again.
And you might be concerned here that it says 26% bad. As long as there's only bad in the warm-up, that's fine. It's just trying to zero in on which parameters for your model make sense. Once zeroed in, you should have 0% bad. So as long as you don't see any bad ones in the sampling phase, it's a sign that your model at least can be computed and worked on. If we look in DrawsDF, you can see I get alpha, sigma, and beta. So I get alpha upper left of our graph, beta upper right, and sigma. And with those 3 latent variables, I can then follow the recipe. You know, the recipe is alpha plus beta times the transformed X value, and get to a life satisfaction score. Like the previous plot I made, this is observed life satisfaction. We're going to try to put a curve of expected life satisfaction through here. That will be my goal. So I'm going to graph mu as a function of X. So if I want to graph mu as a function of X, I need to first pick 20 or so random parameters. I don't want to overwhelm my spaghetti plot that I'm going to do with too many. So I got 20 of the 4,000 draws of alpha, sigma, beta triplets. So my 20 draws are shown, and they're triplets, but to get mu, I don't need the sigma term. I just need alpha and beta. And if I want mu as a function of X, I create this parameterized function where I supply given values of alpha and beta, and I'm going to let the plotting, or ggplot, figure out for each X what's the value of mu. So this will ultimately become a function of just X. And then for any X the plotting software gives, we have to transform it before we put it into mu, because X trans up here has already been through this transformation. So we do the same transformation and run it through. So now we can create an initial plot. If we just look at the initial plot, this is the observed data. And now I'm going to add some layers to the plot for simulated data. Oh, I forgot my get mu function. Let's put that in memory to initialize my plot, add some layers, and we can plot it. and we get a nice curve. Even though we fit a line to our transformed x-axis data, we are able to recapture the relationship on the original scale of GDP per capita compared to life satisfaction. And even though we fit a linear model, we can get this nonlinear result where we see how increasing money tends to lead to diminishing returns in terms of life satisfaction. So biggest bang for your buck is in these early stages, and then you get to a certain point and we trail off. That's the Mr. Money Mustache hypothesis, and at least we have data consistent with it. I hope you enjoyed this investigation of how money impacts happiness. Remember, there's so many other factors. This is not a real study, just illustrative of the power of a linear model, how we can use transformations of the data to make our linear model functional, and then we take that linear model that we fit and put it back on the original scale using the generative recipe. Good luck with it.